Neural networks are everywhere. They're behind image classification, recommendation systems, and even the large language models that we use today. But what actually is a neural network? How does it work? And how can something so simple be so powerful? Today, I want to break neural networks down clearly and visually, using one of the most iconic examples in AI, handwritten digit recognition. A neural network is a function. It takes an input, transforms it, and produces an output. What makes it special is how it's built. It's made up of a lot of neurons. A neuron takes a number, adjusts it using weights, adds a bias, and then decides how strongly to respond using an activation function. When you connect hundreds or thousands of them in layers, the network starts to learn patterns. Layers are where the magic happens. Each layer transforms the data. The first layer learns very simple things. The next layer learns the combination of those. The deeper layer learns the overall structure. This idea actually comes from neuroscience. In the brain, one neuron doesn't really do much, but when you connect millions of them, they create perception, memory, and thought. Artificial neural networks borrows this idea. They take neurons, connect it to layers to learn complex patterns. Let's actually see a neural network in action.
When I draw a digit on this website, the network doesn't see it as a picture. Each pixel becomes a number between 0 and 1 depending on the brightness of the pixel. One image contains 784 numbers, which is the input. These 784 numbers go into the first hidden layer. Each neuron in that layer looks at all the inputs. It uses weights to decide which pixels matter, then adds a bias to adjust how sensitive the neuron is, and then decides how strongly to respond via the activation function. The output of each neuron becomes the input of the next layer, and this continues layer by layer. By the time we reach the output layer, we're down to just 10 numbers, so from 0 to 9. These numbers are turned into probabilities using softmax, which basically turns scores into probabilities for us to interpret. The highest probability is the network's prediction. So if the probability that we drew a 5 is the highest, the network confidently predicts a 5, which in this case is correct.
So how does a network learn in order to make good predictions? At the beginning, the weights are random. So when the network sees a 5, it might confidently say 2. That's obviously wrong. To fix this, we use a loss function that measures how wrong the prediction is. We can also use cross-entropy. Cross-entropy punishes confident wrong answers by increasing the loss. Once we know the loss, we adjust the weights so that the loss gets smaller each time. This is where backpropagation comes in. The network makes a prediction, we measure how wrong it was, we work backwards through the network to figure out which weights cause that mistake, and we shift each weight in the direction that reduces the error via gradient descent.
Who the fuck dare to call me when I'm so busy?
Over many examples, the weights settle into values that make good predictions.
Here's the entire process in summary. You give the network numbers. The first layer looks for simple patterns. The deeper layers look for more complex patterns. The output layer gives probabilities for each digit. Cross-entropy measures how wrong the prediction was. Backward propagation figures out which weights cause the error. Gradient descent adjusts the weights to reduce the error, and this loop repeats thousands of times until the network becomes accurate.